So I made a video all about deriving, so let's do the exact same thing with integration. Again, I will post this, but it is nice to kind of hear me talk through it and help you prepare for the AP test. So first, integration should most be connected with the idea of area. So when we first learned about integration, we really immediately started talking about area under a curve. So ways to find area under a curve. First way is to do it very geometrically, to break it up into figures that we can find the area of using basic geometry. So rectangles, triangles, trapezoids, semicircles. And knowing my integral where it starts and ends, I can add those figures up. Anything that is above the x-axis is considered positive. Anything below the x-axis is considered negative. We then started splitting it up into rectangles. We did Riemann sums with these. So we split it up into rectangles of equal width. We then eventually looked at ones that were split up not evenly, but we used things like my right Riemann sum, so using the right side. We did a left Riemann sum. We did a midpoint approximation, which is using the exact middle of the interval to determine how high it went. Then we started splitting it up into trapezoids. My formula for a trapezoid is 1/2 the height, which is the distance between the x values, times my bases added together, so my b1 plus b2. Those are going to be, again, your y values, how high these bases go up against your x-axis. And then finally, we did integration with boundaries. So once we did all these approximations with rectangles and trapezoids, we then realized if I just integrated something from 4 to 5, and I could do it by hand or with a calculator using the fundamental theorem of calculus, it would give me an exact answer for area under the curve. So some terminology. Antiderivative is another word for integral. Riemann sum is when you're wanting to break things up into rectangles and approximate it. If we talked about inscribed versus circumscribed, inscribed will always be an underestimate. It's going to be drawing our rectangles under a curve. Circumscribed is going to be an overestimate where I'm drawing those rectangles kind of outside the boundaries of the curve. Sometimes they will just say integrate a function and they'll give you a graph instead of giving you an equation and do it maybe geometrically. Sometimes you're given a velocity graph and you're going to be asked something about distance or motion, kind of working backwards from there. There are not many symbols for integration. We basically use the squiggly symbol. We don't have all of the symbols we had for derivatives. Sometimes it has boundaries on it, which means we have to integrate it with the boundaries using my fundamental theorem. Those include a plus c at the end. Sometimes they'll give you the derivative and ask you to work back to the original. Sometimes they'll give you a differential equation that you have to separate and then integrate. As far as applications, motion application is one of the big ones. We should be able to integrate acceleration and go to velocity, and we should be able to integrate velocity to get to position. Area under a curve, area between two curves, all done with integration. Average value is area divided by width. So we integrate to get that area and then divide by how wide the interval is. Volume, which we're getting ready to get into, volume of a disc, volume of a washer, which we'll go through. Cross-sectional volume, I do not think is something I will get to this year. Area is an accumulator. The idea is if I integrate a rate, I will accumulate what happens. So if I have the rate at which cars are going through an intersection, and I want to know how many cars went through the intersection from 2-hour mark to the 5-hour mark, I'm going to integrate that rate using a calculator and put my boundaries as 2 and 5. So integrate to accumulate. So anytime you have something, maybe snow is falling and you have the rate that the snow is falling, if I integrate that in my time interval, it'll tell me how much snow has fallen over that interval. And then when we look at finding solutions, if I integrate to get a particular solution, that means I had to also give you an initial condition to find your C value. So I had to tell you that the function went through the point 3,5 so that I could find my C value when I was done. My techniques of integration, my rules. Power rule is a big one. We did a lot with rewriting with algebra with the power rule. Trig rules take a little bit of getting used to. U substitution was a huge technique that we started with in chapter 4 and continued with in chapter 5, and we did a little bit more in chapter 6. I did not get into much with complete U substitution other than we did ones where you had to switch your boundaries and make everything in terms of U. We learned how to integrate e to the u, du over u. We didn't really do anything with a to the u, but we definitely integrated e to the u and du over u in chapter 5. We can use a calculator to do definite integrals by using the math9 function. Math9, you get f(n)int, and it will evaluate a definite integral for you. You still want to write down your integral on paper if it's a free response. Some strategies to integrating: we can expand, meaning we can distribute, we can FOIL, we can square something out before we integrate. We have some really basic trig identities that help us. I did not do much with add, subtract a constant because that is not something that really shows up on the AP test. I did a ton of pretzeling when you have multiple terms in the numerator and you want to pretzel each piece over the denominator. We did a very little bit with completing the square. It only happens specifically with inverse tangent. That was at the very end of chapter 5. And then we did a little bit with division. That's when we had a bigger degree on top than on bottom. We actually did it synthetically, not with like full long division, so that I could simplify it ahead of time. So those are going through integration. Integration started in chapter 4. We continued a little bit in chapter 5. Chapter 6, we had to integrate when we did separate and integrate. And then chapter 7 are your applications of integration.